And I'm going to introduce our speaker today. Our speaker is Dr. Jonathan Sauder, and he is a mechatronics engineer at NASA JPL, which is the Jet Propulsion Lab out in California. So it's a little bit earlier over there for him than it is for us. He's also a NIAC fellow, and he will tell you a little bit more about what that means later. And he's going to tell us some really, really cool information. I really think this is an awesome presentation, and I hope you will have as much fun as I do. And so with that, I'm going to let you take it away.
So hopefully people can hear me loud and clear. And yeah, so if we're going to explore the most extreme environment in our solar system, the most extreme terrestrial environment in our solar system, we're going to need to take a different approach to our rovers. Hence, in comes Steampunk meeting Spacecraft for the hybrid automaton rover Venus. Now, an automaton is a mechanical robot that we've specifically designed out of high temperature metal alloys to survive Venus's extreme conditions. This is a NASA Innovative Advanced Concept, mission concept, so we're sponsored by the NIAC wing of NASA. And listed here are a number of my collaborators who've worked on this concept. But first, before we get to direct Venus exploration, let's take a step back and look at what inspired this idea for a clockwork mechanical rover that could explore Venus's extreme environment. So the ancients used to look at the night sky and stare at it in wonder and wonder questions like, what's our purpose here? What is our meaning here with these dots of light that we can see? And why do some of those dots of light that we see trace out these unique, intricate patterns in the sky that wander across the sky, not rotating like the other stars do around Earth, but instead tracing out some other pattern and changing where they are in the night sky? To try and understand this, the ancient Greeks invented the Antikythera mechanism, a 2,000-year-old mechanical computer. And this mechanical computer would predict the position of the moon, the sun, the stars. And so you'd basically crank in a date and it would provide output where everything would be expected to be at. However, it may have even predicted where those wandering stars would be, or as we know them today, planets. And of course, since planets are orbiting around the sun, they move different than what the rest of the stars do in the night sky. But what's really exciting is this concept of the Antikythera mechanism might just be the key for us to explore one of those wandering stars or planets. Venus. It has the most extreme terrestrial environment in our solar system. If you go down to the surface, it's extremely hot at 462 degrees Celsius. To put that in context, here's Earth's temperature at 22 degrees Celsius. And Venus is 462 degrees C. Now, I should note, I'm taking this measurement from absolute zero, negative 273 degrees Celsius, because if I was just going from 0 degrees Celsius or freezing, Earth's average surface temperature would barely show up as a blip on the thermometer compared to Venus's extreme temperature. To give you an idea how hard 462 degrees Celsius is to deal with, let's take a look at some different things. So, the most robust off-the-shelf electronic components you can generally buy are mil-spec electronics. Those are only rated to 125 degrees Celsius. Paper spontaneously combusts at 233 degrees Celsius. Lead and solder melt at 300 degrees Celsius, and Venus is even hotter than that. Many of our common aerospace materials, like aluminum that we use in most of our spacecraft, loses all of its structural strength at Venus temperatures. Despite this extreme temperature, and not to mention the pressure that's 92 times that of Earth's, enough to crush the hull of most nuclear submarines, we've actually successfully landed about a dozen probes on the surface of Venus. And these were mostly launched by the Soviet Space Agency at the time, which were the Venera and the Vega missions. And the Venera landers actually were able to land and take pictures. But the longest any of these missions lasted was just 2 hours and 7 minutes before they succumbed to Venus environment. The problem? They overheated and stopped working. Now, that was 30, 40 years ago. Fast forward to today, and our mission concepts haven't gotten much better. The longest that we can survive on the surface of Venus is just about 8 to maybe 24 hours if you're really lucky. And how you do that is you take a sphere and enclose it from the environment, and basically it's a pressurized sphere. Then you put phase change material around it, which is a fancy type of ice that melts at a really high temperature to try and keep that sphere at a cool temperature. And then you let it land, and that phase change material keeps you as cool as long as possible. But even with that, the longest we can get is probably about 12 hours, 24 hours if you're really pushing the limits and can survive some higher temperatures. So why do we want to explore the surface of Venus, or why do we want to spend a long time on the surface of Venus? Well, if you just have a short duration probe, there's a lot of things that you miss on that. What is the weather like on Venus? Is there seismic activity on Venus, and to what extent? You need to sit on the surface for a long time to detect that. What's the makeup of the interior of the planet, and what's geology like across different regions of Venus? All of these, you need to be on the surface of Venus for a long period of time. Further, the current probes only can take sampling from discrete points. Eventually, we want to move to something that can traverse the surface of Venus to be able to explore different aspects of how the geology varies. And we had the same conundrum with Mars. We actually started with probes and then moved on to landers. And Carl Sagan has this great quote in his book, Blues for a Red Planet, where he talks about his frustration at the Mars landers' immobility. I mean, yes, you get to see what's around you, but once you see an environment, you wonder what's just beyond that rock, or what's over that hill. And his ideal tool was a roving vehicle that could traverse the surface of Venus. Now, the Mars rovers, Sojourner, then Spirit and Opportunity, and today Curiosity and Perseverance, are fulfilling Sagan's desires to be able to really help us understand what's going on Mars. But if we want to send a rover to Venus to allow it to explore the surface of Venus, well, the problem is you combine current rover architectures plus Venus, and you get a mission concept that doesn't close. The challenges are that Venus is a high temperature at 465 degrees Celsius. Also, the extreme pressure of 92 atmospheres, 92 times that of Earth's pressure, the corrosive environment from the sulfuric acid, and the 60-day night. What that means is you're going to take a rover and put it on Venus. You have to take a very, very basic functionality approach. Most electronics that we have do not work on Venus. If you were to be able to, there are some silicon carbide and gallium nitride electronics that can work, but they have the processing power about that of a solar-powered calculator. So you really have extremely limited functionalities for a rover. You want to use the wind as a power source, as that's really the only sustainable source of power. I'll talk more about that later. You've got to build it out of titanium and stainless steel, materials that can hold up to Venus's extreme temperatures and also that corrosive environment. And then you need to do short-range detection, obstacle avoidance, and detection for the navigation as you're driving around on the surface of Venus. Because Venus as a planet rotates very, very slowly. That means you have a night which lasts 60 days. That's an incredible amount of time that you have to operate without sun on the surface of Venus. Now, to look for inspiration as to how to redesign a rover on the surface of Venus, we went back to that Antikythera mechanism, because we can build a mechanical computer with gears and mechanisms out of high temperature titanium and stainless steel, which can operate in the Venus conditions. So mechanical computing actually has a great history where it's been used in harsh, high shock environments, used for fire control computers, which would help battleships point their guns in World War II, accounting for things like wind speed, ship speed, and a host of other different factors. This is a differential adder, where you can add two elements in and then get an output, which is the additive result of those two different inputs using a differential. This is a linkage, which is a mechanical multiplier. And you can see here that you've got 2 times 3, which will end up producing an output of 6. And there's all sorts of other mechanisms you can have to do sine functions and integration and any other mathematical function that you possibly would want to do. So we thought we could take these mechanical computing elements, build them out of high temperature alloys and metals, and use them to survive in Venus's conditions. We are also really inspired by the concepts of Theo Janssen, who's recently revived these automata, or mechanical robots, which walk on the beaches of the Netherlands. And they've actually, not only are they pushed and powered by the wind, but they can actually also sense danger. And if they start walking into the ocean, they will turn directions and walk the other way and walk away. So we thought, why don't we create a Strand Beast-inspired mechanical robot for Venus that could walk across the surface of Venus, powered by the wind, able to place instruments and operate for long periods of times. Initially, we think this concept would be 100% mechanical and do everything in a clockwork or steampunk fashion just by brute force, including using a radar target as a retroreflector to communicate with an overhead orbiter. So we had a mission concept, we proposed it to NASA Innovative Advanced Concepts, and they funded us to perform an initial feasibility study. Now, what do you do when you're trying to figure out if a mission is feasible or not, or how to develop a mission? Well, you get a bunch of smart people in the room, and you have them help you invent a concept for what a mission concept for Venus rover would look like. So we actually invited Teo to come and collaborate with us and provide an input on this automaton rover concept. I should note this guy right here is Brian Wilcox. He's one of the inventors of the Sojourner rover, the first rover on Mars. So we were able to pull in a bunch of experts from diverse backgrounds and get them brainstorming as to what really makes sense for a Venus rover that takes this mechanical computing approach. And one of the things that Teo advised us actually was the legs are great and the legs are very beautiful, but the problem with legs is that if you're traveling, they work fine on the flat beaches of the Netherlands, but if we start getting into sand dunes, they stop working as well, and they sort of get jammed up and tripped up on each other. And in fact, if you were to go to an extreme environment like Venus, where you potentially have rocks and craggy environment, they probably wouldn't operate that well. So you probably need to come up with a different concept. He suggested maybe some type of caterpillar tracks. So that led us to starting to get into a mobility trade space and brainstorm what are all the different ways we could have a rover move around the surface of Venus. And we basically came up with two different categories that the rover could operate in. We came up with reactive rovers, which would react to the environment that they are around, basically sense obstacles, back up and avoid, and have to detect the obstacles. And we had a bunch of different ways we could do that. And non-reactive rovers, where the idea was that we would build the rovers that were just robust enough where we didn't have to worry about obstacles. They could just sort of roll over or take on obstacles whatever they would face. So we developed the system into a tank-style locomotion system inspired by World War I tanks that were designed to run across rough terrain and basically wrap tank tracks entirely around our wind turbine, which powered the rover. And the idea was that we could drive over large obstacles using those tank tracks. And in fact, even if we got to a cliff or something like that, the rover could just roll over and just reverse and then keep on driving upside down. And we could design the rover so that it would be robust and resilient to the environment. The idea here is that we could use robustness and resiliency in the design of the rover itself to reduce its complexity. So we moved from an intricate crawler or intricate walker into a sturdy crawling rover with a wind turbine in the center of the concept. So what's the next thing we do now that we have this concept design and we've figured out sort of the size of it and how it would work? Well, next you prototype it. And we started off with some very early and basic prototypes, which you can see here. So first we designed this really small scale rover, which was only about this big. And basically with that, we could adjust the angle of the tank tracks and figure out which angle of tank tracks work best for climbing over obstacles, and how do we want to design this rover such that it can climb over the largest obstacles possible. Then we built a slightly larger prototype. This was about 2 feet by 2 feet or so. And we started, this was large enough where we could drive it around outside. And as we were working on this tank track style rover, we realized there were a few issues. So for one, as you were driving the rover, what would happen is as you would hit a hill, for example, like this, the rover would sort of come up, tilt up, turn around and fall back over on itself, and then just keep on doing that. And you sort of get a washing machine effect where you keep trying to drive over a hill and just keep on going up and over. Now that can be easily solved by having the rover, when it flipped over, by rotating by 90 degrees by having a weight offset. and allow it to continue driving. But the issue that we came up with that was even a little bit more challenging was what happens if we had a rock right in the middle of the rover, right here where the wind turbine is at. That would be sort of the rock between the eyes scenario, and the rover would drive forward and sort of hit that and get stuck on it and couldn't move away from it because there weren't any tracks to climb over it. So we realized that even with a non-reactive style rover, we'd still have to detect and avoid obstacles. We built a bunch of other additional prototypes, like this rover here, which was inspired by the Soviet Mars rover concept, where it's an articulated chassis here that would basically pivot and allow you to climb over very large obstacles, and also prototyped a four-wheeled rover as well. As we built and traded these different rovers, what we ended up realizing is, first of all, the non-reactive rover concepts really didn't work. At any point in time, there was still some obstacles that you had to detect, and you had to have a way of moving around or avoiding those obstacles. As we looked into the reactive rover concepts, what we realized is that there's a lot of great concepts out here, and a lot of these concepts with multiple wheels work great if you have electric motors driving each wheel individually, like the current rocker bogie system for the Mars rovers. But if you're having mechanical power transmission and trying to do something in a high temperature extreme environment, it's best to keep it simple and just go with a four-wheeled rover. During this time of developing the concept, we also became aware of a lot of great work occurring at NASA Glenn on high-temperature silicon carbide electronics. This right here is a mission of their long-life in-situ solar system Explorer. It's a mission that's about a CubeSat size, or a 10 centimeter by 10 centimeter by 10 centimeter block. And this would be a simple weather station that could land on the surface of Venus and last there for multiple days, as long as the batteries would last, because it operates on electronics that are silicon carbide, which can operate at Venus's high temperatures. Now, once again, these electronics are very limited. The processing capability is about that of a solar-powered calculator, so you're very limited in what you can do, but it can be a wonderful science platform to start providing information back. And we thought this right here would be a really good thing to integrate with our current rover concept to develop a hybrid automaton rover. The concept is to have a robust rover that would be mostly mechanically driven, but have a high temperature electronic science package to maximize the science return as we're driving across and exploring the surface of Venus. So this shows a systems diagram of the concept that we came up with. In white, you can see the mechanical elements here, which are mostly the drive system, obstacle avoidance and detection system, and power storage system. And then in orange here, you can see the high temperature electronics, which are as a very basic system where to observe and report. So basically we have a simple clock here that then turns on and off different science instruments, and that science instruments data sort of continuously transmits to an overhead orbiter, which will receive the information. So you're just basically switching through different scientific measurements and transmitting that information as you go. In addition, there's ways that we could possibly take very simple inputs and use that to influence the navigation of the system as well, so that in general, scientists could say, we want to turn 5 degrees to the right or 15 degrees to the left. It's much more like operating a ship, though, than necessarily precisely programming a rover, because you don't have the capabilities to do that on Venus. For the rover itself, we have a wind turbine that takes in the power. That power is split by a differential between the mechanical system and the electrical system, which runs a generator to charge the rover. So we'll talk a little bit more about the different systems as we move forward. But why wind power on Venus? Well, let's talk about power sources for a spacecraft. So your two most common or main power sources for a spacecraft are radioisotope thermoelectric generators, or RTGs. These are basically nuclear-powered batteries that create heat and then use a thermocouple effect to generate electricity. The challenge with an RTG is develop them and to design them safely. They're very expensive to develop, to the fact that currently RTGs are all multi-mission RTGs. What that means, NASA makes an investment in one RTG that'll work in a broad variety of missions across the solar system. The problem is those RTGs have not been designed to operate in temperatures as hot as Venus is. So the packaging doesn't survive in Venus temperatures, because there's only a few places in the solar system where you get to Venus temperatures. Venus, Mercury, possibly the interior of some planets if you're drilling way down, but that's another problem, and near the sun. So because of that, there's a very limited subset of missions that you could do with high temperature RTGs. And because the cost is so high, it really is not a practical approach to plan on having a technology developed for that for Venus. Now, solar power, there are actually solar panels that would work on the surface of Venus, and technologists have shown that they can get solar panels working in Venus environments. The challenge with solar power is the dense, thick cloud cover really reduces the amount of light that you get on the surface of Venus. And further, so like for a 2-meter solar panel, you only get 4 watts of power on average. The other challenge is Venus's very slow rotation rate, or extremely long night. And what that means is you have to go 60 days without solar power. If you look at the history of most of our Mars rovers, they've all stopped working during Martian winter when they can't get enough power. And that's even when the sun's shining on them for part of the day. On Venus, you end up with an environment where you've got 60 days where the sun is not even shining. So the most practical approach is wind power, as you can find places on Venus where there's constant wind. The wind on Venus is slow, about 0.6 meters per second, but it's 10 times more dense than Earth, which means that a slow breeze on Venus is like gale force winds on Earth. So it's almost like being in a strong current of a river. And what we landed on for our rover concept is a 2.6 meter deployable wind turbine to capture the wind energy. So wind is really the only current, sustained, and affordable source of power on Venus. So even with wind power, though, you do have to use that wind power very wisely. And what we found is if we would use the wind power in sort of a more traditional system where you would have that wind energy drive an electric generator, and then that would store the energy in a battery, and then it would then use that battery to drive an electric motor. When you're running a generator motor at Venus temperatures, you get only about 10% efficiency, or you're losing 90% of that mechanical power coming into the wind turbine. Not to mention you're going through a 1 to 100,000 gearbox. Whereas if we directly mechanically use that power to drive the rover, we can directly drive the system, only have frictional losses, and have about a 10 to 1 gearbox. Basically, the Venus wind is low speed, high force, and it makes sense to take that low speed, high force wind in and use that to drive the rover at a low speed, high torque out. The other key thing that we need to do on Venus is to avoid obstacles. Now, the traditional Mars rovers, how they work is they take images of their environment, identify where there's hazards on board with onboard processing, and then plan a path for how to drive around those obstacles. Well, using that approach with cameras and image recognition on Venus doesn't work for 2 reasons. First of all, you've got a 60-day night. That would mean there's half of your mission life that you really couldn't use for long, extended periods of time to move around the surface of Venus. Secondly, solar-powered calculators really can't perform the processing power capable of figuring out obstacle avoidance on Venus, to be able to do image recognition software. Even if there were cameras that could exist, and there's concepts for cameras, but no cameras yet that exist for the Venus environment. As such, you have to do a short-range, direct obstacle avoidance and detection approach. So what does that look like? Well, it looks a little bit different than rovers that we're used to seeing, where we actually just sense the obstacles as we contact them, do a basic backup and turn maneuver, then continue on our path to see if we can have cleared the obstacle or not. If the obstacle is still in the way, we back up, turn again, and then start driving again. And this time, if we've passed the obstacle, we continue to drive. Now, this is an electronic prototype that we built at JPL to demonstrate this concept of sort of this direct short-range obstacle avoidance and detection. So after we proved we could do this with an electrical prototype, we then built a mechanical prototype of this system, which you can see here. So you can see how it hits the obstacle, trips this lever here in the back, which triggers a reverse, and then it drives forward again until it hits the obstacle, triggers the reverse lever in the back, and then you can see this mechanism come around and reset the device to then drive forward again. Now, this is powered by an electric motor, but basically the electric motor just sits where the wind turbine would be applying its input to the rover. So this is a fully mechanical rover except for the power input to demonstrate this concept. Now, as we started to develop this concept, we realized that this system had a lot of sliding components, which leads to a lot of friction. And it's always better to move to a rotary system. So that's where we came up with the planetary reversing gearbox, which you can see here in this video. So basically, you'll notice there's a little button here. And when that button gets pushed, it reverses for a little while to back up the rover and then continues to drive forward. So basically, when we hit an obstacle, we have a bumper which hits this reversing mechanism, and that changes the power input from driving us from going forward to moving into reverse. And here you can see that on the rover concept system here. Now, of course, these rovers that we were developing, these prototype rovers, which this right here is about a quarter scale of what the CAD image is that you saw. But these rovers are made out of plastic and aluminum, materials that wouldn't work in Venus conditions. So in parallel, we were performing an effort to demonstrate how we could get mechanisms to work at Venus temperatures. And to do that, we built a clock to operate in Venus conditions. So this clock had a set of gears on it, a spring to drive it. Turns out it's really hard to get a good springy spring which operates at high temperatures. Most metals just sort of anneal and they stop being a very good spring. Here you can see that clock working at 460 degrees Celsius at Venus temperatures. And then what was also important is to make sure it's working in room temperature environment as well. The other thing we were able to demonstrate with this clock mechanism is the escapement, which causes the tick-tock, tick-tock, tick-tock of the clock, and bearings that would work at Venus's really, really high temperatures. We used a solid film bearing to operate at this. So the next step in our project then was to take the lessons learned that we had from building this mechanism at high temperatures. I should note, the other key thing we wanted to demonstrate with this mechanism at high temperatures was that we could accommodate for the coefficients of thermal expansion, because as you get hot, right, everything grows and expands by a bit. And when you go to 462 degrees Celsius, things can grow and expand by quite a bit, by fractions of an inch. So we wanted to demonstrate that we could still have a precise mechanism working over those temperature changes. And so next what we did is we wanted to combine the lessons learned from our high temperature Venus clock experiment and our mechanical rovers that we showed at JPL and test them in a Venus chamber at JPL. Now this Venus chamber is a 12-inch diameter tube that's about 8 feet long. It's really small because at Venus you have to go to really high pressures. So we wanted to avoid right, you have to have a thick metal cylinder to make sure it doesn't blow up. I mean, this thing is almost basically a bomb inside of it when you're going to Venus pressures. It's hot and it's at 92 times that of Earth's atmosphere. So that's why the space is so constrained. So we had to redesign our rover concept out of the 303 series stainless steel that we developed this clock in and rebuild it to operate in JPL's Venus chamber. Now, the core elements from our system that we wanted to demonstrate was that we could store the energy in the spring, have gears that would operate at Venus temperatures, and this planetary reversing gearbox, and also that we could have a set of sensors that would be able to detect obstacles and reverse when we detected them. So here you see that rover that we specifically designed to fit in the JPL Venus chamber. Now this probably looks like the weirdest rover you've ever seen, but it's a prototype that is designed to operate specifically in JPL's Venus chamber. That's why it's really long and skinny. And this rover has springs, the planetary reversing gearbox right here, and you'll notice that it has a bumper in the front, so it detects the rock at the end, and then reverses, drives forward, detects the rock at the end, reverses, and basically is demonstrating that key functionality. Now, of course, on Venus, we'd reverse and turn and then drive forward again. But given we're driving down a 12-inch chamber, in this case, the problem is that if we were to try and turn, you'd sort of drive up the side of the chamber and might flip over and fall down, which of course wouldn't be desired. So then we were able to test this rover in Venus's conditions. So here you can see it driving to the end of the chamber, detecting the end, backing up, and it's backing up a prescribed number of steps, and then continues to drive forward again, detect the end of the chamber, and then backs up again, demonstrating the core functionality of our rover operating at 460 degrees Celsius in Venus-like conditions. So Actually, it's very relevant as someone asked a question in the chat about what happens if it falls off cliffs. Well, you'll notice the obstacle detection system that we have so far only would detect positive protrusions or things like rocks sticking up in the environment that you can actually detect and back up on. So what we wanted to do is we also realized we need to detect slopes that could cause the rover to tip over if it was too steep, and holes and cliffs. And it turns out holes are a very challenging problem. And we had a few ideas, the team at NASA, is how we could solve this. But one of the things we had discovered is that as I was talking with different people about this Venus rover concept, from watchmakers to artists to people at conferences, everyone got really excited about this concept and would often have different interesting ideas to share about how they could, what you could do with a mechanical rover. There's something about an automaton or a mechanical robot that makes it easy to understand and easy to relate to and contribute ideas to. So we thought, we could come up with one way of maybe doing this at NASA, but this would be a great thing to open up to the general community to see what ideas could they generate and what ideas could they create. So we launched the Exploring Hell Challenge, how to avoid obstacles on a clockwork rover. And we asked people to come up with ideas on how to detect holes and rocks and other obstacles. We launched this in collaboration with NASA Tournament Labs, HeroX, and the Philadelphia Maker Meetup. And so what was really exciting is it wasn't just a team at NASA developing this concept, but the entire community who helped us develop this concept with regards to the obstacle avoidance. And the response was incredible. We got nearly 500 entries for different ways of avoiding obstacles. And I'll show a few of the winners here. So this right here is by an entry by Yosef Gali, an architect from Egypt. And you can see he has a unique tri-wheel design. Basically this allows you to drive over various rocks of different sizes, but also detect small holes, which turned out to be a real challenge. It also has a bumper here to detect rocks that are too high that the rover needs to reverse when it runs into. So you'll see right here is a large rock that triggers the bumper. Then there's a small rock up next that the rover is able to drive over. And then next, there are a series of holes that this specific tri-wheel design can detect. And this tri-wheel design is great because it can specifically go down and detect steep holes, which turn out to be some of the most challenging holes to detect. And are ones that you would need to reverse from while still being able to make it over other holes. So you can see right here, this is a hole where if it was any larger than that, it would need to stop. And that mechanism can actually detect those holes. Then we had an amazing submission from Cobart, a team of artists in Latvia, and they actually built a full-scale prototype here that I'll play in this video. So this shows their slope detection mechanism, which is basically an over-center weight. But their over-center mechanism and their obstacle detection systems all tied into this one device they call the magic pin box, where basically they would have a ball bearing that's triggered to pop up, and when an obstacle is detected, it would pop up and then hit this lever here, which would then send a signal to the rover telling it to back up and reverse. So you'll be able to see it here. They developed a track system as their obstacle detection approach. So if obstacles were small enough, it could be able to climb over them. If the rock was any higher, it would raise up too high, and that linkage would then tell the rover that you need to stop and back up. Same thing went for holes. If the hole was too deep, the sensor would drop in the hole, detect it, and trigger the magic pin box to be able to tell the rover it needed to reverse and back up. So this was absolutely incredible. There's another three winning concepts on the HeroX website that I would encourage you to go to and check out if you're interested in learning more about this. We got an incredible set of submissions here for how to detect these different obstacles on Venus. And that we were able to directly integrate and pull into our concept to be able to then make a concept that could detect those cliffs, holes, and all those various dangerous conditions. The other thing is we were able to involve students in this concept as well, and specifically related to the wind turbine and how to test the wind turbine in Venus-like conditions. So we worked with both Bradley University and California State University, Los Angeles and actually ended up testing a wind turbine in an infinity pool, which is a great surrogate for Venus environments. It turns out he tried to do testing in wind tunnels. You end up having to go to supersonic speeds to sort of simulate the Reynolds numbers in a wind tunnel, and then your effects go nonlinear, and you just really can't simulate things well. So it turns out a water tunnel or an infinity pool is a perfect surrogate for the Venus environment, where you have water traveling through the pool at a decent rate, where you're actually able to test a wind turbine in that simulated Venus environment. So with that, we were able to combine the concepts for the obstacle avoidance system, which then get integrated into the front of the rover, the concepts from our university collaborators on the wind turbine, as well as also the developments on our mechanisms for operating at high temperatures in the mechanical logic system that drive the system into the rover itself to pull together a concept which could one day help us explore the surface of Venus. So now you're probably thinking, this is really awesome and great, but if I'm not a Venus scientist, why do I care? Why is it important to me to send a rover to the surface of Venus, besides being really cool, which it is really cool? But why should I care about sending a rover to the surface of Venus? Well, I'm going to take us back to the beginning of the talk, where I was talking about how the ancients used to stare at the stars in wonder and amazement and wonder questions like, why are we here? Are we alone out here? What is occurring now? And today we stare at the stars and wonder the same questions. Although there's one particular question, are we alone here in our galaxy or in our universe? Are there other places that might have life on them? And that's a big question that a lot of us wonder these days. And in fact, we found some very exciting results as we started to look at different stars in the last 10 to 15 years, and have found that statistically speaking, every star in the night sky has a planet, at least one planet orbiting it. So that means there are tons of exoplanets throughout the galaxy and throughout the universe. And in fact, if you run the numbers and sort of look at what are the potential planets and places that could harbor life, you end up with the potential for billions of Earth-like planets. Now, we don't know which of those, if any, would harbor life on them. But the question is, are there some where life could exist out there? So how do we know which planets might be good candidates for life? Well, of course, we can look at Earth and see where it's at in our solar system, which is known as the habitable zone, where water is sort of the right temperature to be a liquid. And we can understand how Earth works and try to apply that to other planets. But it's also important to understand what doesn't work and why other planets may be less habitable for life that is teeming with life and having a diversity of life on it. And within our solar system, we're very lucky that we have actually 3 planets that are sort of in or on the edge of the habitable zone: Earth, Mars, and Venus. And with this set of 3 planets, we can start to do comparative planetology, right? And look at these planets as examples to be able to understand planets around other stars. And particularly try to explore and understand what makes conditions really good for life on Venus, or on Earth, and not so good for life on Mars and Venus. Now, we know a lot about Earth because that's the planet where we live. We have a ton of missions at Mars. And in fact, you've just sent 3 rovers to Mars this year to try and understand that planet more. But Venus is a mystery. It's been over 30 years since our last mission landed on the surface of Venus. Yet, Venus is a very important planet for us to study because it's very similar to Earth in that it's Earth-sized. It's a lot hotter than what it should be. So the question is, what happened with Venus that it is so hot and that it has a very heavy and thick cloud layer, which basically creates a superheating effect on the planet, because it's much hotter than what it should be than if you put Earth and put it in Venus's location. So the question is sort of, why is there this extreme difference between Earth and Venus? And in a lot of ways, Venus is sort of Earth's evil twin sister that got super hot and less hospitable for life, at least on the surface of Venus, than other environments. So that's why we want to go and explore the surface of Venus. So thank you for listening to this. I'd like to thank the number of individuals who have contributed to this concept, from engineers at JPL to mission architects to artists to clockmakers and watchmakers to students who've all to garage inventors and makers who have all contributed to this concept to build something and help us create a concept for a rover that will hopefully one day explore the system of Venus. And with that, I would like to open it up for questions.
Thank you so much. It's such a fascinating presentation, and it just gets me so excited for space exploration in general, and learning things that we don't know about. Yeah, a planet that, in in the reality of distances in space is pretty close to us, right? And so we did have a couple questions from the chat that popped up. So Evan wanted to know if the test chamber that you use, the Venus test chamber, is that the largest one that there is to test a prototype in?
So the largest test chamber that actually exists is the NASA Gear chamber, which is slightly larger. It's a little bit shorter. It's maybe about 6 feet deep or so, but it's about 2 or 3 feet in diameter, or 3 feet in diameter or so. So it's a little bit larger, but it's still not a huge test chamber. But that is a more accurate simulation of Venus and sort of is the best Venus simulator here on Earth. And it exists over at NASA Glenn. That being said, it's a really nice chamber and actually very expensive to use because of the way it's run. So for this initial test, we wanted to demonstrate it in a chamber that was lower cost to run, and sort of it didn't quite get all the simulation of Venus, but it gets about 70 to 90% of the way there. So
okay. And Nancy had a question about issues with small rocks or dust getting into the mechanism. Is that an issue that you've thought about?
Yes, and that's actually an issue we deal with the Mars rovers as well. And when it comes down to it, you just have to be very careful in how you design your paths for where axles come in and out of the rover. So the goal is that we would have a chassis that's entirely sealed, right? So that would prevent any rocks or dust or anything from getting into the chassis where all the mechanisms would exist itself. And then wherever the axles come out, you actually have to be very careful in how your tolerances align and everything else to make sure that you prevent rocks and dust from getting in there and clogging up the mechanisms. So, and there's various, high temperature composite materials that would be flexible that we could use to sort of getting close around those shafts and prevent dust and debris from getting in.
And I know that when we talked before, I asked you kind of what the timeline would be for maybe the next potential Venus mission like this. Can you talk a little bit about that?
Yeah, so that's another great question. So typically missions, take anywhere between 10 to 20 years in their development cycle. So sort of from where they're at now until they actually launch, it can be a good at least 10 or 15 years. So one of the key things that we've identified with this mission is, to this point, and underneath the sponsorship of NASA Innovative Advanced Concepts, we've shown that we have a way of designing a rover where the design closes and it makes sense, and we can have a rover that operates on the surface of Venus. We've shown that we know how to make mechanisms that work at extremely high temperatures. Then one big thing that's an open area is really getting a good understanding and characterization of the wind. We currently have 4 wind measurements from the surface of Venus, 2 with anemometers, which are the things that spin, have the little cups that spin and actually measure wind from the Venus mission, Venus Venera missions from the Russians, and then 2 that have sort of extrapolated microphone data and tried to use that to understand what the wind speed is. Beyond that, that's very limited, and all those are more than 30, 40 years old. So we have an extremely limited data set when it comes to wind conditions on the surface of Venus. The good thing is those all showed that there was wind, but our models are based off of those, and we need to get more wind measurements from the surface of Venus. So that's where we need some precursor missions, hopefully missions like the long-lived In Situ Solar System Explorer by NASA Glenn, that could come down to the surface, make long-term missions, and help us get better climate models for Venus to understand where are the wind conditions most amenable to a wind-powered Venus rover. And that's probably one of the key things that we'd really need to sell this mission. There's other things that are engineering developments that should be straightforward to do, but those will be things like showing, cycles on gears and bearings for months in Venus conditions, Whereas right now, about the longest that we've had anything operate in Venus conditions continuously is 24 hours. But that tends to be a little bit more of engineering, design, and development work.
And so what kind of information would we want to be gathering from the surface of Venus with a rover like this? And how would it be able to send it back to Earth?
Yes, so the key thing that we want to try to understand is the composition of the rocks across Venus, trying to understand, where did all this carbon dioxide get into the atmosphere and how did it get into the atmosphere? Was it volcanoes or was there something else? And by exploring and understanding the geology of Venus, you can start to get clues at why did Venus become this planet that had this thick carbon dioxide layer that then traps in heat and energy from the sun and makes it superheated on the surface. And so understanding the chemistry and the makeup of rocks is very helpful for that. And then if you can look at that at different locations, it gives you different clues for what happened at different points in time in the timescale of Venus's histories. So that helps to unlock some of the secrets of Venus. I noticed also there was a question on here that I want to make sure we get to, which is the phosphine detected in Venus's atmosphere.
That was my next
This
question.
was a super exciting discovery that came out this fall. And they detected these elements of phosphine, which is a compound that exists, usually it doesn't exist for a long time unless there's something that's generating it. So we don't know where this phosphine is from yet. And there's multiple theories, but one of the ideas is that maybe phosphine could be generated by microbial life in the clouds of Venus. Now, that's a hypothesis currently, and hopefully some future missions to Venus will help reveal and help us understand if there is life in the clouds on Venus. But it's a very interesting discovery that could be an indicator that we could have life in the clouds on Venus. Another interesting, and probably my second favorite fact on Venus, is actually if you go from the surface of Venus 50 kilometers above the surface, right? So that's like, I think it'd be like the equivalent of 2 Mount Everests above the surface of Venus. You actually find a place in the cloud layers that's the most like Earth anywhere in the solar system. You have a pressure about that like Earth. It's sort of like a hot day. So it's sort of like Arizona or something like that, where it's really hot and there's probably a little bit of clouds there, but it's pretty warm, but it's survivable. And the only thing that's the issue at that layer at 50 kilometers above the surface is the sulfuric acid in the atmosphere. But what's cool about that is it's one of the places that exists in our solar system where you wouldn't have to wear a full-on spacesuit. You just have to wear some type of chemical suit and a breathing apparatus to protect yourself. So if you go 50 kilometers above the surface, there's actually a place where you could potentially would be, good candidates and one of the best candidates for places for life currently existing in the solar system, as far as the temperatures and the pressures and other things that exist there, other than the sulfuric acid.
So cool. I think until this talk, I felt like my mission view was very Mars centric, and now I'm just we need to know more about Venus ASAP, right?
Yeah, Venus has been one of the more underserved planets, unfortunately, in recent history. So we really want to get some missions back there. It'll be really exciting and to see what new discoveries are there. I'm hoping phosphine will sort of tip us over the edge of sending a bevy of new missions over to Venus to explore.
Yes, very, very exciting ideas and concepts coming forward, I hope, in the next 30, 40 years. I know when you told me that, I was just like, oh man, it seems so far away, but I know we have some young people here watching, and so maybe they can be inspired and move forward. Speaking to that, several people want to know how to get more involved with stuff like this. We have Eric who wants to know if there are more contests like this, because he works at a place called Inventoy, and they are all Hot Wheels ex-designers, and he says they thrive on tough mechanical challenges, especially RC and rover type challenges. So things like that. And then we have somebody who wants to know what it takes to maybe get to work at JPL and work on the type of things that you're doing.
Excellent. Great question. So first, as far as where can you find additional challenges? Because NASA has a very active prizes and challenges wing. And so if you look up NASA prizes and challenges or NASA's tournament labs, you can find a number of challenges. And usually there's 2 to 3 that are running in parallel at any point in time. Some challenges are sort of smaller challenges, like the Venus rover obstacle detection and avoidance challenge that I had run here. But some are really giant challenges where you could be even designing up to a full spacecraft with either hundreds of thousands or more dollars of prize money being available. So I'd encourage you to check out NASA prizes and challenges and NASA tournament labs for that. I'll try to get a link to place in the chat at the end of this once I stop sharing my screen. The other place too is there's a bunch of vendors that host these challenges, one of which being HeroX. So HeroX has a bunch of challenges, and they have challenges that are not just NASA specific, but challenges from across the industry or industries actually, both private and government industries, and list a bunch of different prize challenges on their website. In the past several decades, it's been realized that having prize challenges can be a very effective way of getting new ideas that are sort of more external and more innovative than sort of the ideas that might be limited or biased from a subset of individuals who have been working on the problem for a long period of time.
Very
cool.
cool.
And I think there was a second part of that question, which is
yeah. So like, how did you get where you are? How can if we have some young people that are looking for a career path, how can they get to where you are?
Awesome. So it generally takes first of all, it depends on what you want to do. I should note that, JPL hires people of all different backgrounds. We have artists and designers at JPL who work on outreach material to engage and work on strategic mission planning as well. We have communications, so English majors who help in writing up stories about what NASA and JPL is working at. And then, of course, we have your standard set of computer scientists and engineers, mechanical, electrical, structural engineers who work on the spacecraft. Then we also have technicians who typically come from more technical fields and help us build the spacecraft. These are like the mechanics who actually put together the bolts and nuts of the spacecraft. A lot of our technicians usually start out in the aerospace industry and they work for different aircraft developers or stuff like that, or work as a mechanic, and then will apply to a job at JPL. A lot of our engineers, you typically have to get a 4-year degree to become an engineer. And then some go in directly out of engineering, out of their undergrad into working at JPL. And then others will work at, will go on to get a graduate degree, either a master's degree or a PhD. Myself, I got a PhD, which is interesting because at JPL, we can really use engineers with both undergraduate degrees and PhDs. The people with PhDs tend to work on things that tend to be more research oriented, like this, whereas the people that have undergraduate degrees will tend to work more specifically on how do we design the rover once we have a concept there, right? So the PhDs tend to often think a little bit more large picture, whereas the engineers with an undergraduate degree tend to focus more on immediate implementation of building the next Mars Perseverance rover. I should also mention, of course, there's a number of scientists who work at JPL who specialize in things like geology or biology, trying to understand, what does life look like on other planets, or what could life look like on other planets, or understanding how do planets behave geologically. And often these sort of people work on the science questions and understanding, why the planets exist as they do. Finally, we have a lot of people in our business departments who handle things like contracts and making procurements and keeping track of making sure that our projects stay on budget and schedule. So there's a lot of people with business backgrounds as well. So there's a wide, broad variety of backgrounds at JPL. You generally have to be, pretty smart. I think JPL requires a minimum 3.0 grade point average. So you want to make sure you know what you're doing. If you're currently looking at applying to schools and you're really interested in getting into space exploration, one of the things you may want to look at is certain NASA centers have strategic relationships with university partners. JPL has 10 what we call SERP schools, Strategic University Research Partners, where we really actively recruit from those schools. We recruit from all schools, right? But we specifically target a subset of schools, including UCLA, University of Southern California, University of Michigan, Georgia Tech, and there's 10 schools total on that SERP list. So if you Google SERP JPL, you can see what are those strategic university partnerships that JPL has. And if you were able to attend one of those schools, you probably have a better chance of making connections with JPL as a whole.
Amazing. It's really inspiring. And I want to thank you again, Jonathan, for being here today, telling us about this. I hope that everybody had as much fun as I did and learned as much as I did. And with that, I want to thank you all for coming. Thank you so much for being here during Astronomy Days at the North Carolina Museum of Natural Sciences. Thank you to North Carolina Space Grant for sponsoring Astronomy Days this year. And we hope to see you at more, including we have astronomy trivia coming up next, right at 6 o'clock. Skelly dropped it in the link if you're interested in coming. Thank you so much again, Jonathan. And I am going to be looking out for some Venus missions in the very near future.
Awesome. Thanks so much. It was a blast on my part to talk with you guys as well and to share this information.
Have a good weekend.
You too.